Hello, friend. Welcome back to this quiet corner of the cosmos. Some nights space feels less like emptiness and more like a conversation we're not quite hearing. Objects pass, stars pulse, and somewhere between those moments, the universe whispers stories about things that were never meant to stay. December 2024. Astronomers noticed something unusual drifting through the outer edges of our solar system. Not a comet they recognized, not an asteroid with a familiar orbit. Just a small, bright point of light moving faster than it should, heading somewhere we couldn't predict. They named it 3IATLAS, the third interstellar visitor we've ever confirmed. Before we drift deeper into tonight's story, if you find comfort in these quiet journeys through science and space, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Now let's drift. Tonight we're following something that doesn't belong to us. A traveler from somewhere else, somewhere unimaginably distant, passing through our solar system like a stranger on a highway who never exits, never slows, never looks back. And here's what makes this story so quietly profound. Even Jupiter, the largest planet we have, the one we've always called the guardian of our solar system, couldn't hold it. You don't need to understand everything right away. Just rest and let curiosity do the listening. Interstellar objects are rare whispers in astronomy. Before 2017, we'd never confirmed a single one. Scientists believed they existed, of course. Mathematically, they had to. In a galaxy with hundreds of billions of stars, objects must occasionally be flung out of their home systems, cast into the void between stars, drifting for millions of years through darkness so complete it's hard for the human mind to grasp. But believing something exists and seeing it are different kinds of knowing. In October 2017, astronomers in Hawaii detected something moving through our solar system at a speed that didn't make sense for a local object. They tracked it backward through space, rewinding its path like a film played in reverse, and realized it hadn't come from our sun. It had come from somewhere out there beyond the edge of everything we call home. They named it 1I, a Hawaiian word meaning scout or messenger from afar. It was long and tumbling, moving at 26 kilometers per second relative to the sun. Fast enough that no orbit could hold it. It came, it passed through, and it left vanishing back into the stellar dark. 2 years later, in 2019, a second visitor arrived, 2I Borisov. This one looked like a comet trailing a faint tail of gas and dust, moving even faster than Oumuamua at 32 kilometers per second. Scientists watched it for months, studying its light, its composition, its path. And then it too disappeared, continuing a journey that began long before Earth existed. And now, 3IATLAS, moving at roughly 34 kilometers per second. Not the fastest we've seen, but fast enough. Fast enough that even when it passed near Jupiter, the giant planet with gravity so immense it shapes the architecture of our entire solar system, Jupiter could do nothing but watch it go. That's the part that feels almost melancholy if you let yourself think about it. Jupiter, massive beyond comprehension. 318 times the mass of Earth, with storms larger than our entire planet. Couldn't slow it down, couldn't capture. It couldn't even bend its path enough to matter. Why not? That's the question we'll explore softly tonight. Not with equations shouted from a chalkboard, but with the kind of understanding that settles in slowly, like realizing something true about the world you've always lived in, but never quite noticed. Here's what most people believe about Jupiter, that it's a protector, a cosmic shield. We've been told, and we've repeated, that Jupiter sits out there in the outer solar system, like a celestial bodyguard catching asteroids and comets that might otherwise threaten Earth. It's a comforting story. It makes the universe feel a little less random, a little more designed for our survival. And there's some truth to it. Jupiter's gravity is real. Its influence is real. Over billions of years, it has captured objects, deflected trajectories, shaped the orbits of countless smaller bodies. But the story isn't quite as simple as Jupiter protects us. In fact, some research suggests Jupiter might send as many dangerous objects toward Earth as it deflects away. Gravity doesn't have intentions. It doesn't guard or threaten. It simply pulls. And depending on where an object is, how fast it's moving, and what angle it approaches from Jupiter's pull can send it tumbling inward just as easily as it can fling it outward. In July 1994, astronomers watched something astonishing happen. A comet named Shoemaker-Levy 9, which had been orbiting Jupiter for decades, finally collided with the planet in a series of spectacular impacts. The explosions were enormous, visible even from Earth, creating dark scars on Jupiter's surface that lasted for months. Here's the thing though, Jupiter didn't protect anyone from Shoemaker-Levy 9. Jupiter had captured it. The planet's gravity had pulled the comet into orbit years earlier, stretching it, breaking it into fragments, and then inevitably dragging it down to a violent end. Protection and presence are not the same thing. Alessandro Morbidelli, a planetary scientist who has spent years studying how planets interact with smaller objects, published research in 2005, showing that Jupiter's role in our solar system is far more complicated than the simple shield narrative suggests. Sometimes it helps, sometimes it doesn't. Sometimes it does both depending on the object and the moment. And when 3IATLAS came through, Jupiter was simply there, a massive presence, but not a barrier, not a trap, not a force strong enough to change the outcome. Because 3IATLAS was moving too fast. Have you ever thought about what it means to escape something, not emotionally, but physically? To move so quickly that gravity, that invisible hand that holds moons to planets and planets to stars, simply lets go. There's a speed for that. A number. Astronomers call it escape velocity. For Jupiter, that number is about 59.5 kilometers per second. If you're at Jupiter's surface or even near it and you're moving slower, then that Jupiter will hold you. Its gravity will curve your path into an orbit, a loop, a return. You'll circle or spiral or fall, but you won't leave. If you're moving faster than 59.5 kilometers per second, though you're free, Jupiter can pull at you, slow you slightly, curve your trajectory a bit, but it can't keep you. You'll pass by, feel the tug, and continue outward into the dark. 3IATLAS was moving at roughly 34 kilometers per second relative to the Sun. That doesn't sound faster than 59.5, does it? But here's the subtlety. 3IATLAS never got close enough to Jupiter for that full gravitational pull to apply. It passed about 5 astronomical units away, more than 740 million kilometers, far beyond the region where Jupiter's gravity dominates. Out there at that distance, Jupiter is still large, still influential, but not enough. Not for something already moving that fast. It's like trying to stop a train by standing on a hill a mile away and waving. Voyager 1. The spacecraft that left our solar system and is now the farthest human-made object from Earth travels at about 17 kilometers per second. To get it moving that fast, NASA had to use a technique called gravity assist, using Jupiter's gravity to slingshot the probe forward, stealing a tiny fraction of the planet's orbital momentum to boost Voyager's speed. New Horizons. The spacecraft that flew past Pluto moves at about 16 kilometers per second. Both needed help. Both needed fuel planning precision. And even with all that, they're still slower than 3IATLAS, which came from the stars with no engine, no plan, just momentum inherited from whatever event flung it into the void, millions, perhaps billions of years ago. 3IATLAS didn't ask permission. It didn't slow down to visit. It simply moved through our neighborhood the way wind moves through leaves present for a moment and then gone. Astronomers using data from the Jet Propulsion Laboratory's Horizon system calculated its path, projected where it came from, where it's going. The numbers are precise, but the origin is a guess. Somewhere out there in some stellar system, we may never identify something happened. a close encounter between planets, a binary star interaction, a supernova's shockwave, and 3IATLAS was sent drifting alone into the space between suns. It traveled for eons, silent, cold, moving at a speed that would carry it across distances so vast, we measure them not in kilometers, but in light years. And then briefly it passed through a small yellow star's planetary system. Ours. We noticed it. We tracked it. We studied it. And Jupiter, massive and ancient, did what gravity does it. Pulled gently, inevitably, but not enough. Not nearly enough. There's something almost beautiful in that. The largest planet we have, the king of our solar system meeting something it couldn't hold. Not because Jupiter is weak, but because the universe is filled with things that don't belong to any single star. Some objects orbit, some objects pass through, and some, like 3IATLAS, exist only to remind us that the space between stars is not empty. It's full of wanderers. We'll continue following this traveler in a moment, tracing the invisible mathematics that decide who stays and who leaves, exploring the strange geometry of goodbye, and learning why speed, not size, writes the final chapter of every cosmic encounter. But for now, just picture it a small, dark object, no larger than a mountain, moving through a system of giants, unbothered, unstoppable, free. So, what does it actually mean to be held by something you cannot see? Gravity is invisible, silent. It doesn't announce itself. And yet right now, it's holding you to your chair, holding the moon to Earth, holding Earth to the sun. It's holding entire galaxies together, across distances so vast that light takes millions of years to cross them. But holding something and keeping it are not the same thing. Think about the moon for a moment. It's been orbiting Earth for over 4 billion years. Every night it rises, crosses the sky, and sets again. Reliable, predictable, held by gravity in an orbit that feels permanent. But the moon is slowly drifting away from us. Every year, the moon moves about 3.8 centimeters farther from Earth. Scientists discovered this by measuring the time it takes for laser beams to bounce off mirrors left on the lunar surface by Apollo astronauts in the 1960s and 70s. The delay gets infinitesimally longer each year. Why? Because the moon is stealing energy from Earth's rotation through tidal forces. Slowly, over millions of years, it's using that energy to push itself into a higher orbit. Earth's gravity still holds it, but the hold is changing, loosening. In a few billion years, if nothing else intervenes, the moon will drift far enough that it won't create the same tides, won't appear the same size, and our sky won't hold the same relationship to our planet. Gravity binds, but it doesn't freeze things in place forever. Here's the misunderstanding most people carry without realizing it. We think of gravity as a kind of cosmic glue, something that sticks objects together. But gravity isn't glue. It's more like a conversation between masses, a constant exchange of influence that depends entirely on distance, speed, and trajectory. When an object approaches a planet, gravity begins pulling on it immediately. But whether that pull results in capture deflection or just a gentle curve depends on numbers. Mathematics. The cold, precise language of physics that cares nothing for what we want to happen. Let's talk about what capture actually requires. In 1846, astronomers discovered Neptune not by seeing it, but by noticing something strange about Uranus. The seventh planet wasn't moving quite right. Its orbit wobbled in ways that Newton's laws of gravity couldn't explain, unless there was another massive object out there, unseen, tugging at Uranus with its gravitational pull. Mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where this invisible planet should be. And when astronomers pointed their telescopes at that exact spot in the sky, there, it was Neptune. Neptune had been there the entire time, held in orbit by the sun's gravity. But until it revealed itself through its influence on Uranus, we didn't know it existed. That's gravity working exactly as the equations predict, predictable, reliable. an orbit that lasts billions of years. But here's what makes Neptune's story relevant to 3I-ATLAS Neptune is in orbit because it's moving at exactly the right speed for its distance from the Sun, about 5.4 kilometers per second, fast enough to avoid falling into the Sun, slow enough that the Sun's gravity keeps curving its path into an ellipse, a closed loop, a return. If Neptune were moving faster, even a little faster, that loop would open. The ellipse would stretch into a parabola and then into a hyperbola, and Neptune would leave. Speed decides everything. When spacecraft engineers design missions to other planets, they spend years calculating trajectories. How fast does the probe need to go? What angle should it approach at? How much fuel will it need to slow down or speed up at critical moments? The Cassini spacecraft, which orbited Saturn from 2004 to 2017, had to be slowed down when it arrived. It was moving too fast to be captured by Saturn's gravity naturally. So engineers fired its engines for 96 minutes straight, burning fuel to reduce its speed, just enough that Saturn could hold it. Without that burn, Cassini would have flown past Saturn and continued into the outer solar system, never to return. That's what we mean when we say gravity doesn't automatically capture things. It's not enough to just be near a massive object. You have to be moving slowly enough that the object's gravity can curve your path into a closed orbit instead of an open one. 3I-ATLAS was never moving slowly enough. By the time it entered the inner solar system, it had been traveling through interstellar space for who knows how long, millions of years perhaps. And in all that time, moving through the near-perfect vacuum between stars, there was nothing to slow it down. No air resistance, no friction. Just cold, empty space and the faint gravitational whispers of distant stars. When it passed near Jupiter, the planet's gravity did pull on it. That's undeniable. Jupiter's mass is so enormous that its gravitational influence extends millions of kilometers in every direction. But pulling on something and capturing it are different outcomes. Imagine trying to catch a baseball thrown at high speed. If it's thrown gently, you can grab it, stop it, hold it. But if it's thrown fast enough, it'll hit your hand and keep going, maybe deflect it slightly, but not stopped. That's essentially what happened with 3I-ATLAS and Jupiter. The object came in too fast. Jupiter's gravity deflected its path by a small amount, less than a degree, but couldn't slow it down enough to trap it in orbit. Here's a question to sit with. Quietly, what if 3I-ATLAS had been moving just a bit slower? What if instead of 34 kilometers per second, it had been traveling at 20 or 15 or 10? At those speeds, Jupiter might have had a chance. The gravitational pull would have had more time to act, more opportunity to bend the trajectory into something resembling a curve that returns. But even then, capture isn't guaranteed. The angle matters. The distance matters. Every variable has to align in a very specific way. Astronomers estimate that for every interstellar object that passes through our solar system, thousands more pass by completely undetected because they're too faint too fast or approaching from angles we're not watching. Avi Loeb and Amir Siraj, researchers at Harvard, published a study in 2019 suggesting that roughly 1 or 2 interstellar objects larger than 100 meters cross inside Earth's orbit every year. Most of them we never see. They come and go in silence. The ones we do catch, like Oumuamua, like Borisov, like 3I-ATLAS, are only visible because we happen to be looking in the right direction at the right time, with sensitive enough instruments to notice something faint moving against the background of stars. But being noticed doesn't mean being held. There's a gentleness to this that's easy to miss if you're only thinking about the mechanics. The universe is filled with objects moving through space, and most of them will never belong to any star. They'll drift between systems' silent passengers in the dark, occasionally passing close enough to a sun to be warmed for a few months before the cold returns. And that's not loneliness, that's just motion. That's the universe being larger than any single gravity well. Even our sun, massive as it is, can only hold objects out to a certain distance. Beyond that distance, other stars start to have more influence. The boundary is called the Hill sphere, and it's different for every object depending on its mass and its distance from other massive bodies. For the Sun, the Hill sphere extends roughly 2 light years in every direction. Beyond that, an object is no longer ours. It belongs to the galaxy. 3IATLAS came from outside that boundary. It entered briefly. It felt the sun's pull, felt Jupiter's tug, pass through the invisible architecture of orbital resonances and gravitational influences that define our solar system's structure. And then it continued outward, crossing back through that boundary, returning to the space between stars. Not captured, not deflected significantly, just acknowledged and released. There's something quietly profound in realizing that most of the universe operates this way. Not through permanent bonds, but through temporary encounters. Objects pass near each other, exchange momentum, alter each other's paths slightly, and continue on separate trajectories. Gravity binds when conditions allow, but when speed, distance, and angle conspire, otherwise gravity becomes just a brief conversation. A momentary pull of force felt, but not sufficient. And perhaps that's enough. Perhaps the universe doesn't need every encounter to result in capture. Perhaps some things are meant only to pass through, carrying information from elsewhere, reminding us that the space we call home is just one small region in an unfathomably vast ocean of moving objects. We'll explore soon the precise mathematics of that motion, the shapes that paths take when they're not quite slow enough to return, and why some curves are written to never close. But for now, rest in this being held and being kept are different things, and the universe is mostly filled with travelers who belong to no one. There's a number written into every goodbye. You can't see it, can't feel it, but it's there encoded in the velocity of moving objects, determining whether an encounter becomes a permanent relationship or just a passing moment in the dark. For 3IATLAS, that number was 34 kilometers per second, 34,000 meters every single second. Fast enough that in the time it takes you to blink, this small object crossed more than 100 kilometers of space. That speed wasn't random. It carried a history. Every object in motion remembers how it began moving. Physicists call this conservation of momentum, and it's one of the most fundamental laws in the universe. Unless something acts on an object to slow it down or speed it up, it continues at the same velocity forever. On Earth, we don't experience this law clearly because we live in an ocean of air. Drop a ball and it falls. Throw a ball and it eventually stops hitting the ground or slowing in the wind. Everything around us is constantly being acted upon by forces, friction, air resistance, gravity, pulling objects toward the planet's center. But in space, there's nothing to slow you down. When NASA launched the Parker Solar Probe in 2018, designed to fly closer to the Sun than any spacecraft before it, engineers had to think carefully about velocity. The probe needed to move fast enough to escape Earth's gravity, but then it needed to slow down relative to the Sun to fall inward toward it. How do you slow down in space when there's no air to brake against? You use gravity itself. The Parker Solar Probe has flown past Venus multiple times using the planet's gravity to steal tiny amounts of orbital energy, gradually reducing its speed relative to the Sun, allowing it to drop into a lower, faster orbit that brings it closer to the solar surface than any human-made object has ever been. At its closest approach, the Parker Solar Probe reaches speeds of about 192 kilometers per second. Not because it has engines firing constantly, but because as it falls toward the Sun, gravity accelerates it. Speed and gravity trade places in a dance that's been going on since the solar system formed. But here's the crucial difference: the Parker Solar Probe is in an orbit, an ellipse, a path that returns. No matter how fast it moves at perihelion, the closest point to the Sun, it's still bound, still held. Because its total energy, a combination of its speed and its distance from the Sun, keeps it locked in a repeating pattern. 3IATLAS had no such lock. When astronomers first calculated its trajectory, they checked the orbital eccentricity. This number, represented by the letter E, tells you the shape of an object's path. If E equals 0, the orbit is a perfect circle. If E is between 0 and 1, it's an ellipse. If E equals exactly 1, it's a parabola, the edge of escape. And if E is greater than 1, it's a hyperbola. 3IATLAS had an eccentricity of approximately 1.03, just barely hyperbolic, just barely beyond the threshold of return. That tiny number, 0.03 above the boundary, represents an enormous difference in outcome. It's the difference between circling forever and leaving forever, between being a comet that returns every few decades and being a visitor who passes through once and never again. Think about Halley's Comet. Eccentricity 0.967. Close to 1, but still less than 1. That fraction of a difference means Halley's Comet has been returning to the inner solar system every 75 to 76 years for millennia. Humans have recorded its appearances going back to at least 240 BCE. Ancient Chinese astronomers saw it. Babylonian tablets mention it. In 1066, it appeared in the sky above England shortly before the Norman conquest, and scribes depicted it in the Bayeux Tapestry. Halley's Comet is bound to the sun, held by gravity in an ellipse so stretched that it spends most of its time far beyond Neptune, in the cold outer reaches, but always curving back. 3IATLAS will never curve back. Its speed combined with its distance from the sun and the gravitational influences of the planets it passed gave it just enough energy to break free. Not dramatically, not with some explosive departure, just a slow, inexorable drift outward that will continue for millions of years until it enters another star system, or doesn't wandering the space between stars indefinitely. The math here is simple, but the implications are vast. Kinetic energy. The energy of motion increases with the square of velocity. That means if you double an object's speed, you quadruple its energy. This is why small differences in velocity create enormous differences in outcome. When the space shuttle used to launch, it needed to reach about 7.8 kilometers per second to achieve low Earth orbit, just 7.8. But to completely escape Earth's gravity and head toward the moon, or beyond, it needed to reach 11.2 kilometers per second. That extra 3.4 kilometers per second required vastly more fuel, more energy, more precision. In 1969, Apollo 10 became the fastest crewed vehicle in history when it reached 11.08 kilometers per second during its return from the moon. The astronauts inside were moving so fast that if something had gone wrong with re-entry, there would have been no second chance. At those speeds, even the angle of approach had to be perfect. Too steep and they'd burn up in the atmosphere. Too shallow and they'd skip off the atmosphere back into space with no way to return. Speed is unforgiving. 3IATLAS wasn't trying to return anywhere. It had no crew, no mission, no destination. It was simply moving as it had been for eons, carrying momentum from whatever event first set it in motion. Scientists suspect that most interstellar objects are fragments from planetary formation. Debris left over when star systems were young, when planets formed from a disk of gas and dust around a new star. Not everything coalesces into stable orbits. Some objects get gravitational assists from massive planets, flinging them outward at speeds high enough to escape. In our own solar system, Jupiter likely flung thousands, perhaps millions of objects into interstellar space during the chaotic early years of planetary formation. Objects that came too close, approached at the wrong angle, or were simply in the wrong place at the wrong time, got accelerated beyond the sun's escape velocity and cast into the void. Somewhere out there, objects that were once part of our solar system are drifting through the galaxy, moving at speeds that ensure they'll never return home. And objects from other systems drift through ours. It's a cosmic exchange, a slow recycling of matter across the galaxy. And speed determines who stays and who leaves. Here's something most people don't realize. You can't just look at an object and know if it's bound or unbound. You have to measure its velocity and its distance from the sun, then calculate whether it has enough energy to escape. When Oumuamua was first spotted in 2017, it took astronomers several days of careful observation to confirm it was interstellar. At first, they thought it might be a comet or asteroid from the outer solar system. Only after tracking its speed and trajectory could they say with certainty this came from somewhere else. The same with 2I Borisov, the same with 3IATLAS. Each time the confirmation came down to velocity, to numbers that don't lie. 3IATLAS entered the inner solar system at a speed that told a story written millions of years ago. Whatever happened in its home system, whatever interaction sent it drifting into interstellar space, gave it exactly enough velocity to cross the distance between stars and arrive here with momentum intact. And when it passed Jupiter, that momentum barely changed. Jupiter's gravity pulled. The object's path curved slightly, maybe half a degree, maybe less. But its speed remained high enough that the curve never closed. The hyperbola remained hyperbolic. In the silence of space math is the only voice that matters. There's no drama in these numbers, no sound, no flash of light marking the moment an object crosses the threshold from bound to unbound. Just quiet mathematics deciding fates across billions of kilometers. And yet, in that quietness, there's something almost beautiful. The idea that speed something as simple as how fast you're moving can determine whether you belong to a star or to the galaxy. 3IATLAS belongs to the galaxy. It came fast and it will leave fast, carrying with it the story of a home it will never see again, moving toward a future written in velocity and distance and the cold, precise language of orbital mechanics. Next, we'll trace the shape of that path, the geometry that defines goodbye, and why some curves in space are written never to return. Paths in space have shapes, not the kind you can easily picture because they exist in 3 dimensions, curving through emptiness in ways that seem abstract until you understand what they mean. But every moving object traces a line through the cosmos, and that line has geometry, mathematics, a shape that tells a story about where it came from and where it's going. Some shapes close, some never do. In the 1600s, long before we had spacecraft or telescopes powerful enough to see distant galaxies, a German mathematician named Johannes Kepler discovered something fundamental about the way planets move. He spent years analyzing the precise observations of Mars made by his mentor, Tycho Brahe, trying to find a pattern. At the time, everyone assumed planetary orbits had to be perfect circles. Circles were divine, mathematically pure, the shape the heavens should prefer. But the data didn't fit circles. Mars refused to cooperate. After years of calculations, Kepler realized the truth. Planetary orbits are ellipses, not circles, but elongated ovals with the sun sitting not at the center, but at one focus point. This was Kepler's first law, published in 1609, and it revolutionized our understanding of motion in space. Planets don't move in perfect loops. They move in stretched curves, sometimes closer to the sun, sometimes farther, but always returning. An ellipse is a closed curve, a loop, a promise of return. But Kepler's work described only objects that orbit. What about objects that don't? That question wouldn't be answered fully until Isaac Newton developed his law of universal gravitation in 1687. Newton's math showed that gravity creates not just elliptical orbits, but a family of curves called conic sections. You can create all of them by slicing through a cone at different angles. Slice horizontally, you get a circle. Slice at an angle, you get an ellipse. Slice parallel to the side of the cone, you get a parabola. Slice steeper than that, and you get a hyperbola. Each shape represents a different relationships between an object and the thing pulling on it. A circle or ellipse means you're bound, held in orbit, destined to return. A parabola means you're exactly at the edge of escape, moving at precisely the minimum speed needed to leave and never come back. A hyperbola means you're moving faster than that minimum fast enough that gravity can barely touch you. 3IATLAS traces a hyperbola through our solar system. The ancient Greeks studied these shapes thousands of years before anyone knew they described the paths of comets and asteroids. Apollonius of Perga wrote an entire treatise on conic sections around 200 BCE, exploring their properties as pure geometry, beautiful abstractions with no apparent connection to the physical world. He couldn't have known that those curves would someday map the trajectories of objects moving through space, guided by invisible forces across distances he couldn't imagine. Mathematics has a strange way of revealing truths before we understand why they matter. When astronomers track an object moving through the solar system, one of the first things they calculate is the shape of its path. They measure its position over several nights, watching how it moves against the background stars, then use those measurements to reconstruct its orbit. For most asteroids and comets, the result is an ellipse. These are the locales, the objects that belong to the sun, circling in patterns that have repeated for billions of years. But occasionally the math produces something different. In 1705, Edmund Halley analyzed the orbits of several historical comets and noticed something remarkable. The comets that appeared in 1531, 1607, and 1682 had very similar orbital characteristics. He proposed they were actually the same comet returning every 75 or 76 years. Halley predicted it would return in 1758. He died in 1742, never seeing his prediction confirmed. But on Christmas night 1758, the comet appeared exactly where Halley's calculations said it should be. That comet now bears his name. Halley's comet follows an ellipse so elongated it spends most of its time beyond Neptune, in the frozen outer solar system, taking decades to make each loop. But it always returns. The ellipse always closes. Other comets, though, follow paths that never close. Comet Hale-Bopp, which blazed across the night sky in 1997, visible even from light-polluted cities, has an orbital eccentricity of 0.995, almost but not quite at the boundary of escape. It will return, astronomers calculate, in about 2,380 years, though its orbit is so stretched that it currently travels far beyond Pluto's distance from the Sun. But if Hale-Bopp had been moving just slightly faster, if its eccentricity had been 1.001 instead of 0.995, it would never return. The ellipse would have opened into a parabola and then into a hyperbola. The difference between a 2,000-year orbit and an infinite journey is sometimes just a few meters per second. That's how delicate these thresholds are. When Oumuamua was discovered in 2017, astronomers calculated its eccentricity at 1.20, distinctly hyperbolic, an open curve, and because hyperbolas don't close, they knew immediately that Oumuamua would never return. You could watch it leave, track its path as it moved away from the sun, accelerating slightly as solar radiation pressure pushed against its tumbling surface, but never slowing enough to turn around. Eventually, it faded from view, too distant and too faint for even our most powerful telescopes. Gone. Not in the dramatic sense of an explosion or collision. Just gone the way a traveler leaves a town visible for a while along the road, then slipping over the horizon. Hyperbolas are the geometry of departure. 2I Borisov, discovered in 2019, had an eccentricity of 3.36, even more hyperbolic than Oumuamua. Its path was so open, so unbound, that it barely curved at all as it passed through the inner solar system. It came, it brightened as sunlight warmed its icy surface. It released gas and dust, like comets do. And then it continued outward the hyperbola, carrying it back into interstellar space. 3IATLAS. With its eccentricity of 1.03 traces, the gentlest hyperbola of the three, just barely open, just barely unbound. If you plotted its path on a graph, it would look almost like a parabola, nearly straight, curving only slightly as the sun's gravity tugs at it. But slight is enough. The curve never closes. The path never returns. There's something quietly tragic about hyperbolic orbits if you let yourself feel it. They represent missed connections, objects passing near enough to interact, but not near enough to stay. Gravity reaches out, pulls, bends the trajectory, but can't quite hold on. And once an object is on a hyperbolic path, there's no mechanism to change it back to an ellipse, not unless something extraordinary happens. A collision, an extremely close encounter with a massive planet, something violent enough to shed velocity suddenly. For 3IATLAS, nothing extraordinary happened. It passed Jupiter at a safe distance. It moved through the inner solar system without hitting anything. And so, the hyperbola remains hyperbolic. In some ways, this makes interstellar objects the loneliest travelers in the cosmos. They don't belong to any star. They move through systems without forming bonds. They're visible only briefly before distance and darkness swallow them again. But maybe loneliness is the wrong word. Maybe freedom is more accurate. Objects on elliptical orbits are bound. They trace the same paths over and over, year after year, millennium after millennium. Predictable, reliable, locked into patterns they can't escape. Objects on hyperbolic paths are free. They go where momentum takes them. They see things no bound object ever will. They cross the boundaries between stellar neighborhoods, carrying information from one corner of the galaxy to another. Witnesses to a cosmic scale no single star system can contain. Which is better? The question doesn't make sense. The universe doesn't value one kind of trajectory over another. Both exist. Both are consequences of the same physics. Some objects loop, some objects leave. And the mathematics that determines which is written in velocity, distance, and mass combined into equations that produce curves, and those curves have names. Ellipse, parabola, hyperbola. Each one a different answer to the same question. What happens when gravity meets motion? For 3IATLAS, the answer is written in the shape of its path, a hyperbola, an open curve, a line that stretches toward infinity. And somewhere along that line, far from here, the object continues moving, tracing geometry through darkness, following a shape that was determined the moment it began its journey, long before it ever arrived in our small corner of the galaxy. The shape was always going to be goodbye. The math knew, even if we didn't. But there's more to this story than just the shape itself. Because Jupiter's influence, though not enough to close the hyperbola, still exists. There's a boundary around every massive object where its gravity matters, where it can whisper to passing travelers, even if it can't hold them. That boundary has a name, and understanding it reveals why some encounters change everything, while others barely register at all. Every massive object in space is surrounded by an invisible border. You can't see it. No line marks where it begins or ends. But cross that boundary, and suddenly the rules change. Gravity shifts allegiance. What seemed like solid influence fades into suggestion. Astronomers call this the Hill sphere, named after George William Hill, an American mathematician who described it in 1878 while studying the moon's motion around Earth. Hill wanted to understand something subtle. How far from Earth could the moon drift before the sun's gravity became stronger than Earth's pull? Where exactly does Earth's gravitational dominance end? The answer wasn't simple, because gravity doesn't have sharp edges. It fades gradually with distance following an inverse square law. Double your distance from an object, and its gravitational pull becomes 4 times weaker. Triple the distance, 9 times weaker. But Hill realized something clever. Even though gravity fades smoothly, there's still a region around every object where its gravity matters more than anything else nearby. Outside that region, other forces take over. For Earth, the Hill sphere extends roughly 1.5 million kilometers in every direction. That's about 4 times the distance to the moon. Inside that sphere, Earth's gravity dominates. Objects there like the moon or artificial satellites orbit Earth more strongly than they orbit the sun. Outside that sphere, the sun wins. Objects might still feel Earth's pull, but they're fundamentally orbiting the sun, not Earth. For Jupiter, the numbers are far larger. Jupiter's Hill sphere has a radius of approximately 53 million kilometers, or about 0.35 astronomical units. To put that in perspective, Mercury orbits the Sun at an average distance of 0.39 AU. Jupiter's gravitational dominance extends across a region nearly as wide as the orbit of the innermost planet in our solar system. That's enormous. And yet, it's still finite. 3IATLAS passed Jupiter at a distance of roughly 5 astronomical units, more than 740 million kilometers, far, far outside Jupiter's Hill sphere. At that distance, Jupiter's gravity was present, technically infinite in reach, as all gravity is, but functionally weak. A whisper, a suggestion, not a command. To understand why this matters, think about what happens inside versus outside the Hill sphere. In 1610, Galileo Galilei pointed a telescope at Jupiter and saw something that would change astronomy forever. 4 small points of light moving around the planet. Not stars because they change position night after night. Moons. He'd discovered Io, Europa, Ganymede, and Callisto, the 4 largest satellites of Jupiter. Today we call them the Galilean moons in his honor. These moons orbit deep inside Jupiter's Hill sphere. Io, the closest, orbits at about 422,000 kilometers from Jupiter's center. Europa at 671,000 kilometers. Ganymede at 1.7 million. Callisto at 188 million. All of them well within the 53 million kilometer boundary. Their orbits are stable, predictable, bound by Jupiter's gravity in patterns that have persisted for billions of years. Io completes one orbit every 1.77 days. Europa every 3.55 days. Ganymede every 7.15 days. Callisto every 16.69 days. You could set a clock by them. In fact, before mechanical clocks became accurate, astronomers used the eclipses of Jupiter's moons to determine longitude while sailing across oceans. The moon's orbits were more reliable than any human-made timepiece. But venture toward the edge of Jupiter's Hill sphere, and things become less certain. Jupiter has 95 known moons as of recent counts. Most of them are tiny, irregular chunks of rock, probably captured asteroids rather than objects that formed alongside Jupiter. And many of these small, distant moons orbit near the edge of the Hill sphere, where Jupiter's gravitational dominance begins to weaken. Their orbits are strange, tilted, elongated. Some orbit clockwise when viewed from above Jupiter's north pole. Some orbit counterclockwise. Some have orbital periods measured in years instead of days. Himalaya, one of the larger irregular moons, orbits at about 11.5 million kilometers from Jupiter, taking 251 days to complete one loop. It's still inside the Hill sphere, still bound to Jupiter, but out there in the borderlands, where the sun's gravity starts to matter almost as much as Jupiter's. Missions like NASA's Juno spacecraft have to navigate these boundaries carefully. Juno orbits Jupiter in a highly elliptical path, swooping close to the planet to gather data, then swinging far out to avoid radiation damage. At its farthest point, it ventures toward the edges of Jupiter's sphere of influence, where orbital calculations become more complex, because you have to account for the sun's pull as well. Engineers call this the three-body problem region, where the gravitational influence of 3 objects, the spacecraft, Jupiter, and the sun, all matter simultaneously. It's the frontier of predictability, the place where simple 2-body orbital mechanics break down and chaos becomes possible. Now imagine you're not a spacecraft under human control. Imagine your 3IATLAS moving at 34 kilometers per second, passing 5 astronomical units from Jupiter. You're not just outside the Hill sphere. You're more than 10 times farther out than the Hill sphere's boundary. At that distance, Jupiter's gravity pulls on you the way a distant lighthouse might pull your gaze. Present, noticeable, but not controlling. The sun's gravity, by comparison, is vastly stronger at that location. You're much closer to the sun than to Jupiter. The sun's mass is about 1,000 times Jupiter's mass. Even though you're on a hyperbolic trajectory relative to the Sun, moving fast enough to eventually escape the solar system entirely in the moment of passing Jupiter, the Sun is still the dominant gravitational influence. Jupiter nudges your path, maybe deflects it by 1/10 of a degree, maybe less, but it doesn't capture you, can't capture you. You're beyond its reach in any meaningful sense. Here's the subtle truth most people miss when they picture gravity size. Alone doesn't determine control. Location matters just as much. Jupiter is massive, 318 times Earth's mass. But if you're far enough away that mass becomes a distant fact, interesting, but not decisive. It's like being pulled by a magnet. Stand close enough, and the pull is irresistible. Step back far enough, and you can feel the tug, but easily walk away. 3IATLAS walked away. Hill's mathematics developed over a century before we discovered interstellar objects predicted this outcome. The equations don't care about drama or narrative. They simply calculate where influence matters and where it doesn't. And for 3IATLAS, Jupiter's influence didn't matter enough. There's a poignancy in that, if you allow yourself to feel it. Jupiter has held so many objects over its history. It's shaped the architecture of the asteroid belt, preventing the formation of a planet between it and Mars through gravitational perturbations. It's captured dozens of moons. It's flung countless comets and asteroids into new orbits or out of the solar system entirely. But when 3IATLAS passed, Jupiter could only watch. The object crossed through a region where Jupiter's voice had once been loud, where centuries ago, rocks and ice chunks felt that gravity as an inescapable pull. But 3IATLAS came from outside. It carried momentum from elsewhere, and by the time it arrived, it was already beyond Jupiter's ability to claim. The Hill sphere is a boundary, yes, but it's also a reminder. Even the largest planets have limits. Even the strongest gravitational fields fade into suggestions at sufficient distance. And space is mostly distance. The region inside Jupiter's Hill sphere, vast as it is, represents only a tiny fraction of the solar system's volume. Most of space exists outside any planet's sphere of influence in the regions where the sun's gravity dominates, or farther out, where even the sun's pull becomes weak and the galaxy's collective gravity takes over. 3IATLAS spent its entire passage through the solar system in these outer regions. It never ventured close enough to any planet to feel a Hill sphere from the inside. It remained always a visitor from the spaces between. Perhaps that's the real story of interstellar objects. Not that they're fast though they are, not that they're on hyperbolic paths though they are, but that they exist in the gaps, the regions between spheres of influence, the places where no single star or planet can claim dominance. They're citizens of the void, and the void is most of the universe. But even in the void, there are patterns, invisible dynamics, the quiet chaos of multiple gravitational fields intersecting, creating regions where small changes lead to large outcomes, where predictability dissolves into probabilities. This is where the mathematics becomes strange, where three bodies create a dance that never quite repeats, and where goodbye becomes not a moment, but a gradual certainty written in the language of celestial mechanics. Chaos doesn't always announce itself with noise. Sometimes it arrives quietly through the slow accumulation of tiny influences, invisible forces pulling in directions that don't quite align, creating outcomes that drift further from prediction with each passing moment. In the case of 3IATLAS, the chaos was mathematical. Three bodies, three sources of gravity, the Sun, Jupiter, and a small object moving between them, subject to both, controlled by neither. This is the problem that has haunted mathematicians for centuries. In 1687, Isaac Newton published his Principia Mathematica, laying out the laws of motion and universal gravitation. With these laws, he could predict the orbit of a planet around the sun with perfect precision. Two bodies, one pulling, one being pulled. The mathematics worked beautifully, but add a third body and everything changes. Newton himself recognized the problem. He spent years trying to understand the moon's motion, which is influenced not just by Earth, but also by the sun. The sun's gravity tugs at the moon, creating small variations in its orbit that Newton struggled to explain fully. He called it the problem which has made my head ache. By the late 1800s, mathematicians had formalized this challenge into what they called the three-body problem. Given three objects in space, each pulling on the other two with gravity, can you predict their future positions exactly? The answer, discovered by Henri Poincaré in the 1890s while studying orbital stability, is unsettling. No, you cannot. Not because the math is too difficult, though it is difficult, but because the system itself is inherently unpredictable beyond a certain time scale. Small uncertainties in the initial conditions, differences too tiny to measure, grow exponentially over time until your prediction becomes worthless. Poincaré discovered that even in a deterministic universe where every force follows precise laws, prediction has limits. This was one of the first glimpses into what we now call chaos theory, the idea that systems can be governed by simple rules and yet produce complex, unpredictable behavior. But here's what makes this relevant to 3IATLAS. The chaos Poincaré described doesn't require violence. It doesn't need collisions or explosions. It emerges naturally from the mathematics of gravity when three or more bodies interact. In our solar system, this happens constantly. The planets orbit the sun in patterns that seem stable, and they are mostly. But they also pull on each other. Jupiter's gravity tugs at Saturn. Saturn tugs back. Earth's gravity affects Venus. Mars feels the influence of Jupiter when they're on the same side of the sun. These perturbations, as astronomers call them, are tiny. A planet's orbit might deviate by a few kilometers over the course of years. But over millions of years, those tiny deviations accumulate. In 1989, astronomer Jacques Lascar published a stunning calculation. Using powerful computers, he simulated the solar system's evolution over hundreds of millions of years into the future. What he found was both beautiful and unsettling. The orbits of the inner planets, Mercury, Venus, Earth, and Mars, are chaotic on long timescales, not wildly unstable, not collapsing, but unpredictable. We cannot say with certainty where Earth will be in its orbit 100 million years from now. The accumulated effects of gravitational perturbations from other planets make precise prediction impossible beyond about 60 million years. Mercury is even worse. Its orbit is so affected by the other planets that there's a small but non-zero chance it could be ejected from the solar system entirely within the next few billion years. This is three-body chaos playing out across geological time. For 3IATLAS, the timescale was much shorter, but the principle was the same. As it moved through the solar system, it felt the sun's gravity constantly. That was the dominant force pulling it along a hyperbolic path. But it also felt Jupiter's gravity, and Saturn's, though weaker. And the sun's gravity wasn't perfectly uniform either, because the sun itself moved slightly tugged by the planets orbiting it. Every influence mattered. Every small force added up. Imagine trying to predict exactly where a leaf will land after it falls from a tree. You can predict the general area. It'll fall downward. It'll probably land somewhere below the branch it came from. But the exact spot? Impossible. Too many variables. Air currents, the leaf's rotation, tiny variations in its shape and weight distribution. Orbital mechanics are more precise than falling leaves, but the principle applies. When multiple gravitational sources compete, even slightly, certainty fades. For 3IATLAS, the largest perturbation came from Jupiter. Astronomers at the Jet Propulsion Laboratory calculated that Jupiter's gravity deflected 3IATLAS's path by approximately 0.2 degrees, 0.2 of a single degree. A change so small you'd need precise instruments to measure it. But even that tiny deflection mattered. Without Jupiter's influence, 3IATLAS would have followed a slightly different path through the solar system. It might have passed a few million kilometers farther from the Sun. Its exit trajectory might have been angled slightly differently, and once it leaves the solar system, that small difference will grow. Over thousands of years, over millions of years, that 0.2-degree deflection will translate into vastly different locations in space. The object might pass near a different star, or avoid a star it would have otherwise encountered. The entire future trajectory of 3IATLAS was altered subtly but permanently by Jupiter's pull. This is what three-body interactions do. They don't necessarily destroy or capture. They nudge, they alter. They write small changes into trajectories that become large changes over time. There's a specific mechanism for this called the Kozai-Leadoff effect, discovered independently by Yoshihide Kozai in 1962 and Mikhail Leadoff in 1961. They were studying how a third body like Jupiter could affect the orbits of smaller objects like asteroids or comets. What they found was fascinating. Even if the third body never comes close, even if it's far away, its gravity can cause the orbit of a smaller object to oscillate. The eccentricity increases, then decreases. The inclination tilts, then flattens. A slow periodic wobble induced purely by gravitational interaction. This mechanism helps explain why some asteroids have such tilted orbits, why some comets swing far out of the solar system's flat plane. The answer isn't that they were knocked there by collisions. The answer is gravity itself, operating over long time scales, creating oscillations that would be invisible on human time scales, but dramatic over millennia. 3IATLAS. Passing through just once didn't experience this effect long enough for oscillations to develop, but it felt the principle. It felt the tug of competing influences. The Sun pulled it forward along the hyperbola. Jupiter pulled it slightly to the side. And those two forces combined created a path that was neither perfectly predicted by the Sun alone, nor perfectly predicted by Jupiter alone. It was a compromise, a negotiation between forces. And in that negotiation, neither force won completely. The Sun didn't capture 3IATLAS. Jupiter didn't deflect it into a new orbit. Instead, the object continued on its way, altered but not stopped carrying the imprint of both influences into the space beyond. Astronomers sometimes describe the three-body problem as a dance. Not a violent collision, but a choreography. Bodies moving in patterns influenced by all the other dancers, never quite repeating, never quite predictable, but still following the music of gravity. For most objects in the solar system, the dance is stable. Planets have been orbiting for over 4 billion years. Their steps are well practiced. The perturbations are manageable. But for interstellar visitors like 3IATLAS, the dance is brief. A single pass through the ballroom, a momentary interaction with the other dancers, and then an exit stage left into the darkness beyond the lights. The chaos in this case didn't create disaster. It simply created farewell. A 0.2-degree deflection. A trajectory altered. A future rewritten in ways we'll never see because the object is moving away from us now, growing fainter with each passing month until our telescopes can no longer track it. Somewhere out there, it continues moving. The hyperbola stretches toward infinity. The perturbations from our solar system fade into memory, encoded in its velocity and direction. And perhaps in a few million years, it will pass through another system, feel another sun's gravity, another planet's tug, and be deflected again, slightly adding another small change to a trajectory that has no end. This is the life of an interstellar object, not bound by any star, not destroyed by any collision. Just moving quietly through a galaxy full of gravitational voices, listening to all of them belonging to none. But not every object has this fate. Some do get captured, rare as it is, and understanding why some stay while most leave reveals the final piece of this story. Capture is rarer than you might think. For every object that becomes bound to a planet or star, thousands pass by without slowing enough to stay. The conditions required are precise, specific, a narrow window in the vast possibilities of celestial mechanics. And yet, it happens. Not often, but often enough that we can study the survivors and ask what made them different. Consider Triton, Neptune's largest moon. Triton is strange. It orbits Neptune backward, opposite to the planet's rotation. Most large moons orbit in the same direction their planet spins, because they formed from the same disk of material that created the planet. But Triton moves the wrong way. This tells astronomers something important. Triton didn't form with Neptune. It was captured. Scientists believe Triton was once a dwarf planet from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Somehow, billions of years ago, it passed too close to Neptune at exactly the right speed and angle. But here's the puzzle. How did it slow down enough to be captured? An object approaching Neptune at high speed should simply swing past and continue on its way. That's what physics predicts. Unless something robs it of velocity, it remains unbound. For Triton, the most likely answer is tidal forces and orbital resonance with other objects. When Triton first encountered Neptune, it probably had a companion, another Kuiper Belt object traveling alongside it. During the encounter, gravitational interactions between Neptune-Triton and this companion transferred energy in complex ways. The companion was flung outward at higher speed, escaping Neptune entirely. Triton, having lost some of its momentum in the exchange, slowed just enough to be captured into an elliptical orbit. Over millions of years, tidal forces circularized that orbit, pulling Triton into the nearly circular path it follows today. But the backward motion remains a permanent signature of its violent capture. This is one way capture happens, through sacrifice. One object gives up energy so another can be held. Another example lives much closer to home, though it's no longer visible. Comet Shoemaker-Levy 9 was discovered in 1993 orbiting Jupiter, not passing by, actually orbiting. Astronomers realized it had been captured sometime in the 1960s or early 1970s, pulled into an elongated ellipse around the giant planet. But the capture was unstable. The orbit brought Shoemaker-Levy 9 dangerously close to Jupiter during each pass. In July 1992, the comet ventured inside Jupiter's roche, limit the distance at which tidal forces become stronger than an object's own gravity. The comet broke apart into more than 20 fragments, creating a string of icy pearls orbiting Jupiter. 2 years later, in July 1994, those fragments collided with Jupiter one by one over the course of a week. Astronomers around the world watched as each impact created explosions larger than Earth, leaving dark scars on Jupiter's atmosphere that persisted for months. Shoemaker-Levy 9's capture lasted barely 3 decades. From capture to destruction, the entire relationship played out faster than a human lifetime. This shows the fragility of capture. Even when it succeeds, it doesn't guarantee permanence. Jupiter has irregular satellites that tell similar stories. Moons like Pasiphae and Ananke orbit far from Jupiter in retrograde paths, moving backward like Triton around Neptune. Their orbits are tilted, elongated, unstable on geological timescales. These are almost certainly captured objects, asteroids that wandered too close and through some combination of circumstances lost enough velocity to be held. But their orbits are precarious. Simulations suggest some of these moons might be ejected from Jupiter's system within the next 100 million years. They were captured once, but they might not stay captured forever. So, what exactly does it take for capture to succeed? First, you need low relative velocity. The object must be moving slowly relative to the planet. If it's too fast, no amount of gravitational attraction will prevent it from leaving. Second, you need a close approach. The object must come within the planet's sphere of influence, close enough that the planet's gravity dominates over other forces. Third, and most critically, you need a mechanism to shed velocity. Something has to slow the object down during the encounter. In the case of Triton, that mechanism was a three-body interaction. In the case of temporary captures like Shoemaker-Levy 9, the mechanism was repeated passes that gradually stole orbital energy through tidal forces. Another mechanism is atmospheric drag, though this only works for small objects approaching planets with thick atmospheres. A small asteroid passing through Earth's upper atmosphere might lose enough velocity through friction to drop into orbit, though it would likely burn up or crash rather than achieve a stable capture. For 3IATLAS, none of these mechanisms applied. It was moving too fast. Its closest approach to Jupiter was too distant, and there was nothing to rob it of velocity. No atmosphere to drag through. No companion object to interact with. No repeated close passes to gradually steal momentum. Just a single flyby, fast and far, leaving the hyperbola intact. Planetary scientist David Nisvorny published research in 2018 analyzing the probability of capture for interstellar objects passing through the solar system. His calculations showed that capture is extraordinarily rare. For every 10,000 interstellar objects that enter the solar system, perhaps one might be captured, and even then, probably only temporarily. The vast majority simply pass through and leave. The numbers are unforgiving. But temporary capture does happen more often than permanent capture. An object might be caught in a chaotic orbit for a few months or years, circling the sun or a planet in an unstable path, before perturbations from other bodies eventually kick it back onto an escape trajectory. In 2020, astronomers discovered an object they designated 2020 SO, which appeared to be orbiting Earth. For several months, it followed a peculiar path around our planet, close enough that some called it a mini-moon. Analysis of its orbit suggested it wasn't a natural asteroid, but actually a rocket booster from the 1960s. Surveyor missions temporarily captured by Earth's gravity after decades drifting through space. By March 2021, Earth's gravity released it, and 2020, so returned to orbit around the sun. Temporary capture, a brief gravitational embrace, then farewell. Even our moon, stable as it seems, is in a kind of slow-motion farewell. It's drifting away from Earth at about 3.8 centimeters per year, stealing rotational energy from our planet through tidal forces. In billions of years, if the sun doesn't destroy both bodies, first the moon might drift far enough to weaken Earth's gravitational hold significantly. Capture, it seems, exists on a spectrum, from permanent and stable to temporary and chaotic, to barely there whispers of influence that fade almost immediately. 3IATLAS fell into the final category. Barely influenced, barely deflected, never close to being held. It lacked the three ingredients for capture: too fast, too distant, nothing to break against. And so, it remained free. There's something almost poetic about that. The idea that freedom in space is just a matter of velocity and distance. Move fast enough, stay far enough away, and even the largest planets become scenery rather than captors. 3IATLAS carried that freedom from its origin wherever that was. Some planetary system millions or billions of miles away, where a gravitational interaction sent it flying into interstellar space. And it will carry that freedom forward into whatever future awaits it in the galaxy beyond our view. Perhaps it will pass near another star in a few million years. Perhaps that star will have planets. Perhaps one of those planets will be massive like Jupiter and will try as Jupiter tried to slow it down. And perhaps it will fail as Jupiter failed. Because 3IATLAS is not an object looking for a home. It's an object already at home in the spaces between stars, where no single gravity well can claim dominance, where motion is the only constant, and where the galaxy itself is the only structure that matters. That's the nature of interstellar objects. Not lost, not seeking, just traveling. And in traveling, they remind us that most of the universe operates this way. Most objects belong to no star. Most paths lead nowhere in particular. Most meetings are temporary. Capture is the exception. Passage is the rule. Yet even knowing this, even understanding the mathematics that make capture so rare, there's still something worth exploring about the nature of these visitors themselves and what their brief presence in our solar system tells us about the galaxy we inhabit. The galaxy is filled with wanderers we've never seen. For every interstellar object we detect passing through our solar system, hundreds, perhaps thousands, slip by unnoticed. Too faint, too fast, moving through regions of space we're not watching at the right moment. They're everywhere, astronomers now believe. A vast population of homeless objects drifting between stars, carrying no allegiance to any sun, witnesses to parts of the galaxy we'll never visit. Until 2017, this was all theory. We assumed interstellar objects existed because the math demanded it. When planetary systems form, they're violent places. Giant planets migrate inward and outward, flinging smaller objects into the void. Simulations showed this had to happen, but assumptions aren't discoveries. On October 19, 2017, astronomer Robert Warwick was reviewing data from the Pan-STARRS telescope in Hawaii when he noticed something unusual: an object moving through the inner solar system at a speed that didn't fit. Its trajectory didn't make sense for anything bound to the sun. Within days, astronomers around the world were tracking it, calculating its orbit, measuring its light. And the conclusion was unavoidable. This object came from outside our solar system. They named it 3IATLAS, the first confirmed interstellar visitor. Oumuamua was strange in almost every way. It tumbled end over end, reflecting light in patterns that suggested an elongated shape, possibly 10 times longer than it was wide. Some scientists compared it to a cigar. Others suggested it might be flat, like a pancake tumbling through space. It showed no signs of outgassing, no tail, no coma of gas and dust, like comets produce when heated by the sun. And yet, as it moved away from the sun, it accelerated slightly, pushed by some force astronomers still debate. Solar radiation pressure, perhaps. Or outgassing too faint to detect. Oumuamua passed through the inner solar system in a matter of weeks, moving at 26 kilometers per second relative to the sun. By the time astronomers confirmed what it was already leaving, growing fainter with each passing day. It's now beyond Neptune's orbit, heading toward the constellation, Pegasus, moving through space at a speed that will carry it to another star's neighborhood in roughly 20,000 years. We'll never see it again. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered a second interstellar visitor using a telescope he'd built himself in Crimea. This one looked more familiar. It had a tail. It was clearly a comet releasing gas and dust as sunlight warmed its icy surface. Astronomers designated it 2I Borisov and studied it intensely for months as it passed through the inner solar system. Spectroscopic analysis showed it contained molecules similar to comets from our own Oort cloud, but also differences. Hints of a chemistry shaped by a different star's light, a different formation environment. Borisov moved even faster than Oumuamua at 32 kilometers per second relative to the sun. Its orbit was more steeply hyperbolic, an eccentricity of 36 compared to Oumuamua's 1.20. It came, it brightened, it faded, and like Oumuamua, it left. Now, 3IATLAS, the third confirmed visitor, moving at 34 kilometers per second with an eccentricity of just 1.03, the gentlest hyperbola of the three. 3 visitors in 7 years. And this is almost certainly just the beginning. In 2019, astronomers Amir Siraj and Abraham Loeb from Harvard published calculations suggesting that interstellar objects pass through the inner solar system far more often than we realized. Their models indicated that at any given time, there might be one interstellar object within Earth's orbit and several more in the outer solar system. Most of them we simply don't see. Our telescopes aren't sensitive enough. Our surveys don't cover enough of the sky. and these objects move quickly, visible for only weeks or months before they fade beyond detection. Siraj and Loeb estimated that roughly 1 or 2 interstellar objects larger than 100 meters pass inside Earth's orbit every year. Every year. That means, during the time you've been alive, dozens of visitors from other star systems have passed through our neighborhood without us noticing. Silent travelers moving through a solar system that barely acknowledge their presence. This changes how we think about the galaxy. For most of human history, we imagine star systems as isolated islands. Planets orbit their star, moons orbit their planets. Everything stays local, bound by gravity into stable families that persist for billions of years. But the discovery of interstellar objects reveals a different picture. Star systems aren't islands. They're more like rest stops on a cosmic highway, places where travelers pass through briefly before continuing their journeys. And the highway is crowded. Astronomers now estimate there could be trillions of interstellar objects larger than a kilometer wandering through our galaxy. Trillions. Most of them fragments from planetary formation flung out of their birth systems during the chaotic early years when giant planets were still migrating. Some might be intact dwarf planets like Pluto-sized bodies ejected completely from their home systems. Some might be comets carrying water ice and organic molecules across interstellar distances. Some might be rocky asteroids, chips of stone that once orbited stars now hundreds of light years away. And all of them are moving, slowly by human standards, but constantly. Crossing the galaxy at speeds of tens of kilometers per second, covering light years over millions of years, occasionally passing near stars and planets that tug at them gently before releasing them back to the void. The Vera Rubin Observatory, currently under construction in Chile, will change our ability to detect these travelers dramatically. When it becomes operational, it will survey the entire visible sky every few nights, sensitive enough to detect faint, fast-moving objects that current telescopes miss. Astronomers predict the Rubin Observatory will discover approximately 1 interstellar object per year, possibly more. Within a decade, we might have a catalog of dozens of visitors, each with its own trajectory, composition, and story. And each one will tell us something about planetary systems beyond our own. When we analyze the composition of interstellar objects, we're sampling material from star systems we can't visit. The molecules we detect, the ratios of elements, the structure and density, all of these provide clues about how other systems formed, how they evolved, what kinds of planets they contain. Oumuamua's strange shape and lack of outgassing raised questions about its composition. Was it made of solid rock, metallic icy, but too depleted to show activity? We still don't know. Borisov's spectroscopic signature showed it was rich in carbon monoxide, more so than typical comets in our solar system. This suggests it formed in a colder environment, farther from its parent star, where carbon monoxide ice could condense. 3IATLAS, still being studied as it moves outward, will add another data point. Another piece of the puzzle. Each visitor is a sample returned from the galaxy, without us having to send a spacecraft billions of kilometers to collect it. They come to us. And while they don't stay, their brief presence is enough to measure, to analyze, to learn from. There's something humbling about this. The realization that we're not at the center of anything. Our solar system isn't special. It's just one of hundreds of billions of star systems in the galaxy, and objects from elsewhere pass through regularly indifferent to our presence. They don't arrive with fanfare. They don't announce themselves. They simply move through the space we happen to occupy, following trajectories determined millions of years ago by forces we'll never witness. Most of them will continue to miss. Even with better telescopes, even with more sensitive surveys, the majority of interstellar visitors will pass undetected, too small, too faint, too fast. But the ones we do catch offer a glimpse into the larger structure of the galaxy. They remind us that matter moves between stars, that planetary formation is a messy process that produces debris, that the space between suns is not empty, but populated with fragments of systems we'll never see. 3IATLAS is one of those fragments, a piece of somewhere else. A wanderer with a story that began in a star system whose location we can't determine, moving through space on a path that will carry it past other stars in the distant future. And somewhere along that path, perhaps a few million years from now, it might pass through another solar system. Another set of planets might feel its presence briefly. Another civilization, if one exists, might detect it moving through their neighborhood. And then it will leave them to continuing the journey that seems to have no destination, only motion. But before we let 3IATLAS fade completely from view, there's one more layer to this story, worth sitting with. Quietly, a reflection on what it means for something to pass through without leaving a mark, and why that might be exactly the point. There's a word we don't use enough when talking about the universe: transience. Everything passes, everything moves. Even the things that seem permanent, the stars we navigate by the constellations we've named, are slowly drifting, changing position so gradually that human lifetimes can't perceive it. In 13,000 years, Polaris will no longer be the North Star. The Earth's axis wobbles in a slow circle called precession. And that wobble shifts which star sits above our North Pole. Ancient Egyptians navigated by Thuban, a star in the constellation Draco. Future civilizations, if they exist, will navigate by Vega. The permanence we feel when we look at the night sky is an illusion created by our brief perspective. 3IATLAS understands this in a way we struggle to. It doesn't orbit, it doesn't return. It exists only in motion, only in the act of passing through. And perhaps that's not a limitation. Perhaps it's a kind of freedom we're not wired to appreciate. Think about Voyager 1 and Voyager 2, the two spacecraft launched by NASA in 1977. Both have now left the solar system, crossing into interstellar space. Voyager 1 in August 2012. Voyager 2 in November 2018. They're the only human-made objects to have done this. And they did it intentionally, carrying golden records with sounds and images from Earth messages for any civilization that might find them billions of years from now. But here's what makes them different from 3IATLAS. Voyager 1 is moving at 17 kilometers per second. Voyager 2 at 15 kilometers per second. Both slower than 3IATLAS's 34 kilometers per second. We built the fastest objects humanity has ever created, pushed them with every bit of energy and precision our technology could manage, and they're still slower than a random chunk of rock that wandered into our solar system, carrying nothing but momentum from an event we'll never witness. That's humbling. Voyager 1 will pass within 1.6 light-years of the star Gliese 445 in about 40,000 years. Voyager 2 will come within 7 light-years of Ross 248 in roughly 40,000 years. These aren't destinations. The spacecraft won't slow down or enter orbit. They'll just pass by silent and dark. Their power supplies long dead, their instruments frozen. Interstellar passage. The same fate as 3IATLAS, except the Voyagers began their journey with purpose, and 3IATLAS began with accident. Does that difference matter to the universe? Probably not. Both are objects in motion. Both trace paths through the galaxy that will last for millions of years. Both carry information, though the Voyagers carry it intentionally. And 3IATLAS carries it in its composition, its structure, the story written in its atoms. In February 1990, as Voyager 1 was leaving the solar system, astronomer Carl Sagan convinced NASA to turn the spacecraft's camera around one last time and photograph Earth from 6 billion kilometers away. The result was the famous pale blue dot image. Earth appeared as a tiny pixel, a fraction of a point of light, suspended in a beam of scattered sunlight. Sagan wrote about that image. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. That perspective, that sense of smallness, is what interstellar objects give us without trying. 3IATLAS doesn't care that we're here. It doesn't notice our telescopes pointing at it, recording its position, calculating its path. It moves through our solar system, the way you might walk through a city without noticing individual ants on the sidewalk. Not with malice, not with indifference even. Just with a scale mismatch so complete that awareness isn't possible. And yet we noticed it, we tracked it, we studied it, we gave it a name, in some small way that matters, not to 3IATLAS, but to us. Because every time we detect one of these travelers, every time we calculate an orbit that proves something came from beyond our solar system, we're reminded that our neighborhood is not isolated. We're a part of a larger structure, a galaxy, where matter moves between stars, where planetary systems exchange debris across distances measured in light years and time scales measured in millions of years. The Oort cloud, the vast sphere of icy bodies surrounding our solar system, at distances up to 2 light years from the sun, probably contains objects that didn't form here. Visitors that arrived millions of years ago, moving slowly enough to be captured by the sun's weak outer gravity, settling into long, stable orbits that will last until some future perturbation sends them flying again. And objects from our Oort cloud, nudged by passing stars, occasionally fall inward, appearing as long-period comets that take thousands of years to complete a single orbit. It's a slow exchange, a cosmic recycling program operating on time scales that make human history look like a blink. 3IATLAS participated in that exchange for a brief moment. It passed through. It felt our sun's warmth for a few months. It experienced a gravitational tug from Jupiter that altered its path by 1/10 of a degree. And now it's leaving carrying that tiny change forward into a future we can't predict. By 2027, it will have crossed beyond the orbit of Neptune. By 2030, it will be farther from the Sun than Pluto. By the mid-2030s, it will fade beyond the reach of even our most powerful telescopes, becoming just another invisible object in the dark. But it won't stop. It won't slow down. It will continue moving at 34 kilometers per second, crossing roughly 1 light year every 9,000 years. In 100,000 years, it will be 10 light years from here. In 1,000,000 years, 100 light years. In 10 million years, 1,000 light years, having crossed a significant fraction of our region of the galaxy. And during that journey, it might pass near other stars, other planetary systems, other worlds where perhaps beings with telescopes might notice a faint object moving too fast to belong to them. They might give it a name, calculate its trajectory, wonder where it came from, and then watch it leave just as we did. This is the life of an interstellar object, not defined by where it is, but by the fact that it's always leaving, always arriving somewhere else, always in between. There's a Zen quality to that existence if you let yourself feel it. No attachment, no permanence, just motion. Just the endless present of traveling. We humans struggle with this. We build homes. We form bonds. We create structures meant to outlast us. We want things to stay. We want orbits that close relationships, that return patterns we can rely on. But the universe operates mostly on open curves, on hyperbolas, on paths that lead away from every origin, never returning, never completing a loop. 3IATLAS doesn't struggle with this. It simply is. Moving, existing. A small piece of rock and ice tracing a line through space that began before Earth had humans and will continue long after we're gone. And maybe that's the real lesson here. Not that we're insignificant, though we are small. Not that the universe is indifferent, though. It doesn't care about our stories. But that passage is enough. That moving through even briefly, even without leaving a lasting mark, is a valid way to exist. We noticed 3IATLAS. We measured it, we learned from it, and soon we'll let it go because we have no choice. It was never ours to keep. Perhaps nothing is. Perhaps the solar system, the galaxy, the universe itself all operate on this principle. Things arrive, things leave. And the space between arrival and departure, that's where existence happens. Not in the permanence, but in the passing. So, tonight as you rest, as you let these ideas settle into the quiet spaces of your mind, consider this you too are passing through. Not just through this moment this day, but through existence itself. Every atom in your body was forged in a star billions of years ago. Those atoms will outlast you, returning to the universe, perhaps becoming part of new stars, new planets, new forms of existence you can't imagine. You're not so different from 3IATLAS, a temporary arrangement of matter moving through space and time, following a path shaped by forces you didn't choose. And that's not sad, that's not lonely, that's just true. The universe is full of travelers. Some orbit, some pass through. Some, like 3IATLAS, remind us that the space between stars is not empty, and the journey without a destination is still a journey worth taking. 3IATLAS is out there now, growing fainter, growing distant, but still moving, still free, still following the hyperbola written into its motion millions of years ago. We'll never see it again. But we saw it once. We noticed a stranger passing through our neighborhood, and for a brief moment, we shared the same space. And then, as all things must, it continued on its way. Thank you for drifting through this story with me tonight, for letting these quiet thoughts about motion and meaning settle into the spaces where sleep begins. There are countless other stories written in the sky, countless other travelers we've yet to notice, and countless mysteries still waiting in the dark between stars. Perhaps on another quiet night, we'll explore them together. Until then, rest well, dream gently, and remember, even in passing, even without returning, you were here, you were noticed, you mattered. Good night.